The Cretaceous didn't kill you with size first. It killed you with patience. Before the giants entered the picture, before the ground shook under something that weighed 8 tons, there was something watching you from the tree line. Low to the ground, still, calculating the exact moment your attention shifted. The predators that dominated the understory of the Cretaceous weren't the largest animals in the ecosystem, and that's precisely what made them so effective. Velociraptor is the obvious entry point, though the animal most people picture is wrong. The Hollywood version, sleek, human-sized, dramatically lit, is a creative interpretation of something considerably more grounded and, in some ways, more unsettling. The real Velociraptor mongoliensis stood roughly half a meter at the hip. Turkey-sized, feathered, built for low-clearance terrain in what is now the Gobi Desert. If you saw one in isolation, your first instinct might be to dismiss it. That instinct would be the last mistake you made, because Velociraptor almost certainly didn't operate in isolation. Trackways preserved in stone across multiple sites show small dromaeosaurids moving in coordinated patterns that don't resemble solitary hunting behavior. Whether this constitutes true pack intelligence in the mammalian sense is still debated. But the physical architecture of the animal tells its own story. Velociraptor had binocular forward-facing vision, meaning genuine depth perception, a trait almost exclusively associated with predators that need to judge distance accurately during a strike. The sickle claw on its second toe, long misrepresented as a slashing weapon, functioned more like a climbing hook and a pinning device. It held prey down while the animal used its jaws. The killing was deliberate and close. Now scale that up slightly and move it into the forests of late Cretaceous North America. Troodon formosus, or the broader category of troodontid hunters it represents, operated in a different register entirely. Troodon had the largest brain-to-body ratio of any known non-avian dinosaur. Its eyes were enormous relative to skull size, forward-facing, and structured in a way that strongly suggests low-light efficiency. Current analysis points toward Troodon as a crepuscular or fully nocturnal hunter, which means while every other large animal in the ecosystem was navigating darkness as a liability, Troodon was navigating it as an advantage. It didn't avoid the night. The night was the strategy. Think carefully about what that means in practice. Most large herbivores in the Cretaceous, your best-case scenario as a theoretical visitor, had vision calibrated for daylight. Threat detection dropped significantly after dusk. Herd behavior provided some protection, but herds sleep, and they don't sleep uniformly. Troodon didn't need to overpower anything. It needed to be patient, precise, and invisible until the moment it wasn't. At that point, the engagement was already over. The coordination element is where this gets genuinely difficult to process. Modern birds demonstrate sophisticated social hunting behaviors. Harris's hawks coordinate aerial approaches in dense terrain. Corvids communicate about threats and relay that information across individuals who weren't present for the original encounter. There is no scientific reason to assume dromaeosaurids and troodontids lacked analogous behavioral complexity. The neurological architecture was there. The social grouping evidence is there. What emerges from that combination isn't just a predator. It's a distributed threat system that could track you, flank you, wait you out, and respond dynamically when you change direction. You couldn't bluff your way past it. You couldn't climb above it. Several of these animals were capable climbers. You couldn't wait for dawn if true dawn was involved, because dawn was when true dawn finished, not when it started. The predators in this size class didn't need to be as large as you to be more dangerous than you. They needed to be more coordinated, more patient, and more adapted to the specific terrain than you were. They were all three. And they weren't even the apex threat in the ecosystem. They were the baseline. There is a specific moment in a large predator encounter, documented in modern prey animals and consistent enough to be considered a behavioral pattern, where the prey stops attempting escape and enters a physiological state closer to shutdown. It isn't a decision. It's a neurological response to the recognition that the energy cost of continued flight exceeds any realistic probability of survival. The animal simply stops. Researchers who study lion and crocodile predation have noted it repeatedly. The prey doesn't die fighting. It dies having already calculated at some level beneath conscious thought that fighting was no longer a viable option. Tyrannosaurus rex did not need to be fast to trigger that response. The popular debate around T-Rex locomotion, was it a hunter or a scavenger, how quickly could it move, has distracted from something more functionally important. T-Rex had a chemosensory system, specifically olfactory bulb development, comparable in relative scale to modern vultures and some shark species. It could smell carrion or living prey from substantial distances. Its hearing was calibrated toward low-frequency sound detection, the kind of sound produced by large animals moving through vegetation, by footsteps on compressed earth, by breathing. It had forward-facing eyes with overlapping fields of vision, providing genuine binocular depth perception across a longer focal range than most theropods. T-Rex wasn't just powerful. It was a long-range detection platform attached to a body that weighed somewhere between 8 and 14 tons, depending on the individual specimen. The bite force measurements are worth pausing on, because numbers don't fully convey what they mean physically. Estimates for adult T-Rex bite force range from 35,000 to 57,000 newtons. Figures derived from jaw musculature volume, bone stress modeling, and the fossil evidence of what those jaws actually did to other large dinosaurs. Healed bite marks on Triceratops bone indicate T-Rex was biting through the frill and crest of a 3-ton ceratopsian, and the animal was surviving the encounter, at least initially. Which means the bite force wasn't the ceiling of what it could do. It was just what it chose to apply at moderate effort. The teeth themselves were not blade-like and slicing in the way most theropod dentition was structured. They were conical, robust, designed for bone penetration and structural destruction rather than clean cutting. T-Rex wasn't trying to open an artery. It was trying to compromise your skeletal integrity. There's a clinical difference between those two goals, and only one of them is worse. Territory scale matters here in a way that doesn't get enough attention. Based on isotopic analysis of T-Rex fossil sites and comparison with modern large predator-ranging behavior, individual animals likely covered territories measured in hundreds of square kilometers. This means that your plan, find the open terrain, navigate around the predator, put distance between yourself and the threat, was operating against an animal whose operational range you were almost certainly already inside. The territory wasn't something you encountered at a border. It was something you were already standing in. Now leave North America and move to Cretaceous South America, roughly 97 million years ago, Giganotosaurus carolini. Estimates place it between 12 and 13 meters in length, potentially exceeding T-Rex in raw linear scale, though with a somewhat lighter build. The skull was longer, reaching up to 1.8 meters, and the jaws were structured differently. Where T-Rex was built for bone-crushing compression, Giganotosaurus had blade-like, laterally compressed teeth designed for slicing through large volumes of tissue quickly. The leading hypothesis for its primary prey is sauropods, titanosaurs specifically, animals that could reach 30 to 40 tons. Giganotosaurus didn't hunt things its own size. It hunted things that dwarfed it. That predator-prey relationship tells you something important about what it was built to handle and what your 70-kilogram theoretical body represented on its sensory register. Not a challenge, a footnote. Africa answered with Carcharodontosaurus saharicus, comparable in size to Giganotosaurus, operating across the river systems and coastal plains of what is now North Africa during the Cenomanian Age. The name translates directly, shark-toothed lizard. The dentition confirmed it. Large, serrated, recurved teeth, optimized for penetrating and tearing through the hide of enormous sauropods. Spinosaurus shared the same ecosystem, which produced one of the more striking ecological realities of Mesozoic Africa. The apex predator niche was, at various points, occupied simultaneously by multiple animals in the 12 to 15 meter size class. The system didn't have a single dominant threat. It had several, distributed across different habitat zones and prey specializations, with significant geographic overlap. What all three of these animals share, beyond raw scale, is a specific quality that makes them categorically different from the intelligent, coordinated hunters in the previous chapter. With Velociraptor and Troodon, there was a cognitive dimension to the threat. You were being outthought. With T-Rex, Giganotosaurus, and Carcharodontosaurus, cognition mostly stops being relevant to the outcome. These animals didn't need a strategy for you specifically. You were below the threshold of complexity that required one. A T-Rex navigating its territory wasn't hunting you in the active, coordinated sense that a pack of dromaeosaurids was hunting you. It was simply moving through space, and if you occupied the same space, your presence resolved into a straightforward biological outcome that required minimal adjustment on its part. The modern analogy that comes closest isn't a lion or a crocodile. It's closer to being in the operational path of something with no particular interest in you, but no particular reason to redirect either. The indifference, in some ways, is the most difficult part to sit with. The intelligent hunters in Chapter 1 were paying attention to you specifically. That was terrifying. These animals were not paying attention to you specifically. That was worse. There is documented behavior in large modern predators, specifically in cases where prey is detected but not immediately pursued, that researchers describe as interest without urgency. The predator acknowledges the presence, continues its current activity, returns its attention at an interval of its own choosing. Modern crocodilians do this with striking regularity. There is strong behavioral and neurological basis for assuming large theropods operated similarly. The pursuit didn't begin when you were detected. It began when the animal decided it was convenient. You had no mechanism to influence that timeline. You couldn't negotiate the distance, couldn't change the terrain fast enough to matter, couldn't produce a threat display that registered as meaningful to an animal that spent its life navigating conflicts involving multi-ton ceratopsians and armored ankylosaurs. The scale differential didn't just make you physically outmatched, it made you communicatively irrelevant. You had nothing to say to it that it was built to hear. And that was still only the open terrain. You hadn't tried the forest yet. The forest felt like an answer. After open ground, after the exposure of flat terrain with nothing between you and something that could detect you from a kilometer away, the tree line looked like logic, density, cover, broken sight lines. Every survival instinct calibrated by millions of years pointed toward vegetation as refuge. Get into the trees, reduce your visual profile, use the environment as a buffer. It was a reasonable conclusion drawn from accurate premises. The problem was that the forest had already been occupied, for considerably longer than your instincts had existed, by animals that had built their entire hunting architecture around exactly that reasoning. You didn't find cover in the Cretaceous forest. You entered a pre-constructed trap. Carnotaurus sastri is where this becomes structurally uncomfortable. Operating across late Cretaceous South America, roughly 70 million years ago, Carnotaurus was a medium to large abelisaurid theropod, approximately 8 to 9 meters in length, built with an unusual combination of features that don't immediately make anatomical sense until you understand what they were for. The arms were almost completely vestigial, reduced to a degree that exceeded even T-Rex's forelimb reduction. The skull was short, deep, and heavily reinforced, with 2 prominent brow horns that gave it an immediately recognizable silhouette. None of that is the important part. The important part is the musculature of the tail and hind limb complex. Carnotaurus had an unusually developed cauda femoralis muscle system, the primary locomotion engine in theropod dinosaurs, that biomechanical modeling suggests enabled extremely rapid acceleration over short distances. Not sustained speed, burst speed. The distinction matters enormously in forested terrain, where pursuit distances are short, and the ability to cross 5 to 10 meters in a fraction of a second is worth considerably more than the ability to sustain a chase across open ground. Carnotaurus wasn't built to run you down across a plain. It was built to cover the distance between concealment and contact before your nervous system had fully registered that something had moved. Modern ambush predators follow this exact mechanical template. The common thread isn't speed in absolute terms. It's the ratio between reaction time and closing distance. If the predator can cover the space between you before your motor system completes the command to move, speed becomes irrelevant as a survival variable. Carnotaurus appears to have been built around that specific ratio in an environment, dense forest, limited sight lines, broken acoustics, where that ratio was most exploitable. Now introduce the question of what you actually see in a Cretaceous forest before something moves. The answer, in most scenarios, is very little. Modern tropical forests reduce visibility to tens of meters in many directions. Cretaceous forests weren't structurally identical to modern ones. Flowering plants were still diversifying, the understory composition was different, but the fundamental visibility problem remained. Dense canopy, irregular ground cover, inconsistent light penetration. Your detection range in that environment dropped to the point where by the time you registered a threat, the distance that remained between you was already within burst speed territory for an animal built like Carnotaurus. You weren't getting early warning. You were getting simultaneous warning and contact. Allosaurus fragilis complicates this further, though it operated earlier. Late Jurassic, roughly 155 to 150 million years ago, across the floodplains and forested river margins of what is now the American West. Allosaurus was larger than Carnotaurus, reaching 9 to 12 meters, and built along different mechanical lines. Where Carnotaurus was a burst ambusher with a reinforced skull, Allosaurus had a skull engineered for a specific and deeply counterintuitive hunting behavior. The jaws were relatively lightly constructed for an apex predator of its size. Finite element analysis, the same structural modeling used in engineering to test load tolerances, showed that the Allosaurus skull would have performed poorly under the compressive stress of a power bite. It wasn't built to clamp down and hold. It was built to hatchet. The leading model for Allosaurus predatory behavior involves using the skull as a high-speed axial weapon, dropping the upper jaw into prey with the neck musculature providing the driving force, rather than closing the jaw against resistance in the way a crocodilian or T-Rex would. This would allow Allosaurus to inflict massive tissue damage in a single strike without requiring sustained grappling contact, which is biomechanically expensive and exposes the predator to injury from struggling prey. Strike, withdraw, follow. The forest environment made this strategy geometrically practical. Dense vegetation funneled prey movement into predictable corridors. You weren't navigating freely in forested terrain. You were following paths of least resistance, the same paths that had been walked repeatedly by every animal in the ecosystem, the same paths that Allosaurus had been observing and waiting along for exactly that reason. The vegetation that felt like protection was functioning as a channel system, routing you toward contact. There's a behavioral concept in predator ecology called the landscape of fear. The idea that prey animals don't experience an environment as neutral terrain with occasional danger, but as a continuous gradient of risk that shapes every movement decision they make. Prey animals in high predation environments don't go to certain water sources. They avoid specific vegetation densities. They modify their grazing patterns based on sightline availability rather than food distribution alone. The landscape of fear isn't metaphorical. It's a measurable, documentable shift in spatial behavior driven by predation pressure. In the Cretaceous forest, that landscape was structured almost entirely against you. The high-risk zones, dense cover, narrow corridors, low visibility approaches to resources were precisely the zones your instincts were directing you toward. Every place that felt safer was, by the ecological logic of that environment, more dangerous. And the forest didn't just contain ambush predators. It contained their blind spots, which were your blind spots too. Sound behaved differently in dense vegetation. Directional audio became unreliable, distance estimation degraded. The acoustic signatures of something moving through undergrowth blurred into background noise. The same broken sightlines that prevented you from seeing a predator prevented you from accurately locating one you'd already heard. You couldn't triangulate. You couldn't assess distance. You were navigating on incomplete information in an environment that had been optimized through millions of years of predator-prey pressure to keep that information incomplete. The tree line wasn't a refuge. It was the hunting ground. You just didn't know that until you were already inside it. Everything so far assumed one thing, that whatever kills you is trying to. A predator choosing you, tracking you, closing distance. The intelligent hunters targeted you. The apex predators registered you as food. The ambush specialists positioned themselves where you'd pass. In every case, your death was intentional. The herbivores didn't work that way. Triceratops horridus didn't want anything from you. It weighed 6 to 12 tons, stood around 3 meters tall, and carried horns up to a meter long, backed by a reinforced skull built to absorb and redirect force. It was, functionally, a living weapon that spent most of its time eating plants, until you were too close. The danger wasn't hunger, it was proximity. Large herbivores operate on threat thresholds, distances where your presence triggers a response calibrated for real predators. Modern examples make this clear. Elephants initiate charges at tens of meters, buffalo attack before you realize they're there, and hippos kill more humans than lions. The pattern is consistent. These animals don't scale their response to your actual threat level. A triceratops didn't evaluate you. It applied the same solution it used for T-Rex, several tons of mass accelerating at speed, ending in a meter-long horn. The fact that you weren't a threat wasn't relevant. Ankylosaurus magniventris approached the same problem differently. Instead of forward offense, it was a mobile fortress with a tail club, a fused mass of bone capable of generating forces strong enough to fracture theropod legs. The armor covered nearly every angle. The underside was the only vulnerability, which required flipping a multi-ton animal, something even large predators struggled to do. For you, the important part was simpler. The tail didn't need to hit precisely. It swept wide. A threatened ankylosaurus wasn't aiming. It was responding, with a weapon capable of catastrophic damage to anything in range, and it didn't even have to be reacting to you. That's the pattern across large herbivores. The danger is indirect. Stampedes make this obvious. When one animal reacts, the herd follows before verifying the threat. Hundreds of tons of moving mass don't need intent. Anything in their path is resolved the same way. Hadrosaurs added another layer. Species like Parasaurolophus likely used low-frequency calls to communicate across distance, meaning a disturbance could spread through the group rapidly. You didn't need to trigger the herd, you just needed to trigger one animal. After that, the system handled the rest. The result is something with no clean modern equivalent. Today, ecosystems separate threats, predators to avoid, herbivores manageable with distance. The Cretaceous didn't. These herbivores carried weapons designed to survive T-Rex. Applied to you, they were disproportionate. You didn't have to be prey. You didn't have to be targeted. You didn't even have to make a mistake. You just had to be there. The Cretaceous wasn't hostile to you specifically. It was indifferent to you completely. And in an ecosystem running at that scale, indifference was enough.